Hello friends, welcome to the online lecture series of digital communication. We are studying fifth module of unit number 5th, that is passband digital transmission. Today we are going to discuss ary PSK. But before that, let's have a quick revision that what we have studied in last lecture. In last lecture, we have studied DPSK, that is differential phase shift keying. In differential phase shift keying, as we know, it is a non-coherent version of your BPSK. Since it is going to use a differential encoding and combining with phase shift keying, that's why it is called what? Differential phase shift keying. So in that encoding, the binary input, the next bit of binary input, it is going to depend on the what? Output of the previous encoded bit. So if we are going to combine this type of differential encoding with PSK, it would become DPSK. After that, we have seen the generation and the detection of DPSK. And we have also seen, we have proved that reconstruction of your DPSK signal, it is invariant with the choice of your starting bit, initial bit. Because we have seen with logic bit 0 as a starting bit and bit 1 as a starting bit, and at the end we got the same binary reconstructed input what we have transmitted. So we have proved that it is independent of the choice of your initial bit. After that, we have seen the advantages, that what are the disadvantages of your DPSK. Then we came to know that it has been used, its applications, it has been used in your wireless LAN, Bluetooth, RFID. And at the last, we have compared DPSK with your BPSK. So it's about our previous lecture. So now let's start our today's topic. Today we are going to discuss ary PSK generation and detection. Then we are going to see the geometrical representation, power spectral density, and advantages and disadvantages of it. Now starting with our today's lecture, that is ary modulation techniques. Now the word binary, it is going to represent 2 bits. That's why 2 bits, it means the possible outcomes, the symbols, it could be what? 0 or 1. But over here, M array, it means M, it is going to represent a digit that corresponds to the number of conditions or levels or combinations possible for a given number of binary variables. This is the type of digital modulation technique which is used for what? Data transmission, in which 1 bit, 2 or more bits are transmitted at a time. As a signal, single signal is used for multiple transmission and the channel bandwidth is what? Reduced. Now we are going to see the M array equation. Now if a digital signal is given under 4 conditions, such as your voltage level, your frequency, it could be your amplitude or phase, then M it would be equal to what? 4. Now the number of bits necessary to produce a given number of condition, it is expressed mathematically as n is equal to log of m to the base 2. Now what is this n and m? Whereas n, it is a number of bits which is required, and m is the number of conditions or levels or combination possibilities with your n bits. Now this above equation, it could be rearranged what? 2 raised to n equal to m. So for example, if 2 raised to 2 it is equal to there, then output would be 4. It means 4 conditions are possible. As we have seen in QPSK, that is quadrature phase shift keying, it is a special class of your M ary PSK because it has more than 1 bits. So M over here it will equal to what? 4. Why? Because n number of bits per symbol is equal to 2. So the possible combinations, it could be 0, 0, 0, 1, 1, 0 or 1, 1. Now suppose if n equal to 3 over here, then 2 raised to 3 is equal to what? 8. So such 8 possible symbols are there. So since each symbol, it is going to be represented by 3 bits, because n equal to over here what? 3 bits. So it could be 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1 up to 111. So here total 8 possible symbols are there, and each symbol, it consists of what? 3 bits, that is n bits. So over here n could be anything. It could be 16 array, right? So n, it could be 2, it could be 3, it could be 4, like that one. In general, multi-level M-array modulation techniques are used in digital communications as the digital inputs with more than what? 2 modulation levels, which are allowed on the transmitter's inputs. And hence, these techniques are what? Bandwidth efficient. There are many M-array techniques are there, and some of these techniques, modulate, it is going to modulate one of the parameter of carrier. It could be your amplitude of the carrier or phase or frequency of the carrier. But today we are going to see M-array PSK system. So, but basically what are the types of M-array systems? M-array PSK, M-array QAM, that is quadrature amplitude modulation, and M-array FSK. So as I told, today we are going to discuss what? M-array PSK. Now what are the features of M-array PSK? Now this envelope, it is constant with more phase possibilities. Second, this method, it was used during the earlier days of space communication. Definitely M-array PSK, it has a better performance than your amplitude shift keying and frequency shift keying, and it has a minimal phase estimation error at the receiver. The bandwidth efficiency of M-array PSK, it decreases, and the power efficiency, it is increases with increase in M, that is possible symbols. Now we are going to see the transmitter. As this block diagram you can see on the screen, this B of t, this B of t, that is a bit stream, it is applied to what? This serial to parallel converter, and this block, it can store the n bits of a symbol, and these n bits, that is per symbol, have been presented serially in time sequence one after the other, and then the n bits per symbol are first assembled by this block, that is serial to parallel converter block. Then all these bits are presented at once on this n output lines of the converter. You can see that is the, since one symbol, it consists of what? N bits. So after getting the n bits serially, this block, it is going to make the available all the bits what? Parallelly at the output, right? So thus the n bit message, it appears in the parallel form at the output of this serial to converter, serial to parallel converter block, and the output of this block, it is going to remain unchanged for a duration of what? N TB. What is n? N, it is the number of bits, and TB, it is what? It is a duration of each bit. So NTB, it is nothing but your what? Symbol duration, which is definitely symbol duration. It is a time required for this converter to assemble a new group of n bits, right? So after, we can say, every NTB seconds, after every symbol duration, the converter output is updated. Since this n bits per symbol, it is going to be present at the output for a duration of what? N TB, right? And after NTB, you would get the new input and the new output, it would be updated at this output of this converter block. Now, the n bit output of the converter is applied to what? Then digital to analog converter. Now, depending on the n bit digital input, it is going to produce analog voltage, that is VA. And as we know that n bit digital input, it can have 2 raised to n equal to what? M. Just in previous slide we have seen M, which is nothing but your that M number of possible combinations. Hence, this D to A converter output, VA, it would have M number of distinct values depending on the symbols, because M different symbols are there. So corresponding to that different symbol, the analog voltage definitely it would be different, which is corresponding to that particular symbol. So finally, this analog voltage, it is applied to what? Sinusoidal or sine wave generator, right? Which produces what? Constant amplitude sinusoidal output voltage, and the phase, that is maybe phi m, or which is going to be determined by this what? D to A converter output, that is VA. So thus at the output of the transmitter we get a what? Fixed amplitude sinusoidal waveform, but the phase of which has 1-to-1 correspondence to this n bits per symbol. And remember, it is going to change only once per symbol duration, that is Ts. What is Ts? Ts equal to NTB. And in this manner, this M ary PSK is generated. Now, after understanding M ary transmitter, hope so you understood how the function it is going to take place, right? So basically this analog voltage, it is going to depends, it has a different value for different symbols because total M symbols are there, right? So, and this is the M ary PSK output. Now we would see now that how the receiver, PSK receiver, it is going to function. Now you can see on the screen that M ary receiver it is there, M ary PSK receiver it is there. It is going to operate on the principle of what? Synchronous demodulation, which we discussed for, if you remember, for BPSK and QPSK we discuss. And the carrier recovery system, see this is your carrier recovery circuit it is there. So it will require a device, which can raise the received signal to the mth power. See this M ary PSK, it has been given to this input of this block, which is going to receive to the what entry, raise it your receive signal to what? Mth power. Now this signal, it is applied to what? Band pass filter, and which has a center frequency what? MFC. And at the filter output, we get a what? Sinusoidal at a frequency which is what? MFC, right? What is the frequency? MFC. That is the what? Mth harmonic of your carrier frequency. Now this MFC is given to what? Frequency divider circuit. Now since it is divided by M, so what is remain? FC. So what would be the output of this block? It would just FC. So two carriers are going to produced at the filter output. You can see that is cos omega CT, and next it is your sin omega CT. So these are the two recovered carrier. Then these recovered carriers are applied to two multipliers, balance modulator. See, cos omega CT, it is given to the second multiplier, and sin omega CT, it has been given to your first multiplier. And the other input, what are the other input? You can see the other input to the each multiplier block is connected to, see this, received M array PSK signal. Getting that it has been given to what? Received M array PSK signal. Now the output, this is the output. Now the outputs of these balance modulators are applied to this integrator. This is first integrator and this is second integrator. Since this M array PSK, it is what? Non-offset or non-staggered type. So it is going to work along with what? Bit synchronizer, right? But for the simplicity, we are not going to show this one. Then the outputs of this integrator, that is TSPE and TSPO, which is even bit stream and odd bit stream respectively. And since it is a non-offset, it is there. So these outputs are applied to what? Analog to digital converter, right? So analog to digital converter, which is going to yields what? It is going to produce what? N bit transmitted signal. This is 0 to n minus 1, that is total n bit, right? So this signal, it is converted to again your bit sequence, what we have transmitted by using what? Parallel to serial converter, right? So if n equal to 4, then 2 raised to 4, it would be what? 16. So it is, and as we know, the bandwidth, we will see that the bandwidth of this M array PSK, it is what? FB by 2, that we are going to see it now. So hope so you understood this your M array PSK. It is just simple that this is your carrier recovery circuit, it is there, that you have to remember. Then the two different carriers are applied to your balance modulator, and another input to this balance modulator, it is your definitely your M array PSK, whose output given to this integrator, and output of these integrators are given to A to D, which is converts your data into your digitally, and then you would get your bit sequence by means of this parallel to serial converter. Now we are going to see the geometrical representation of your M array PSK signal. As you know, in quadrature phase shift keying, that we have grouped together two bits to form messages, right? That is 0 0 0 1 1 0 and 1 1. These are the four possible combinations of your QPSK, which has a duration of your what? 2 TB. Why 2 TB? Because each symbol, it is going to consist of 2 bits, and if it is m bits, 3 bits, then it would be 3 TB. So depending on the bits, the symbol duration, it is going to decide, and it is having a particular phase shift which is transmitted. As we know, the QPSK signal, it is going to be differed by your pi by 2 radian in phase with respect to each other. So this same principle, it can be extended to your M array PSK. Just instead of 2, we have to take n equal to more than 2, greater than 2. So M array signals are obtained. How we are going to obtain? Now see, by grouping n bits to form a n bit symbols. And these symbols, it is going to extend over a duration of what? N TB. And TB, it is nothing but your duration of 1 bit. Due to the grouping of this n bits per symbol, so how many symbols we could have? 2 raised to n equal to m. So guys, M array PSK, it is simple as your QPSK. Just instead of 2, we have to raise the number of bits. Now these M symbols, as it is going to be represented by the sinusoidal signals, which is of duration of Ts equal to NTB. Ts, it is what? Symbol duration, which is equal to NTB, and TB, it is a duration of 1 bit. So which differ from one another by a phase of 2 pi by m radians. What is m? It is m, it is nothing but your possible symbols, right? 2 raised to n equal to m. Now, mathematically, how we can represent this one? So, if you remember that PSK equation, that is for VM array PSK, how could we write it? That's square root of 2ps cos omega ct plus phi m, where m is equal to what? It is from 0, 1, 2 up to m minus 1. So in equation 1, this phi m, it is going to represent the symbol phase angle, which is given by 2m plus 1 pi by m, right? If you remember, in QPSK system, what we have written? We have written 2m plus 1 pi by 4. Why 4? Because there were 4 possible symbols for there. But over here we don't know. So we are going to represent the symbols by m. M possible symbols are there. So that's why this phi m, it would be what? 2m plus 1 pi by m. Sorry, it is 0, 1, 2 it is there. So please note it down. Up to m minus 1, that is m total symbols are there. So hope so you understood this equation of your M array PSK. It is same as your QPSK, but QPSK, the bits are defined, that is 2, and possible symbols are 4. That's why we have written 2m plus 1 pi by 4. But over here we don't know how it could be the n, it is going to change. So this pi by m we have taken, which is nothing which is going to represent what? Symbol phase angle. Now, the signal space diagram in which the coordinate axes are formed by this orthonormal waveform, that is u1 of t and u2 of t, we in previous lecture we already came to know that is u1 of t, which is also represented by phi1 of t. It is given by what? Square root of 2 by ts cos omega ct, and u2 of t or phi2 of t, it is given by square root of 2 by ts sine omega ct, right, which has unity energy. Now the distance of each M array PSK from the origin, it is given by what? Square root of ES. Now ES, what it is? What it is? A symbol per energy per symbol. So it is what? Represented by PS into TS. Remember, we are going to use S over here, not B, because it is we are going to use for duration of TS, right? So this is the geometrical representation of your M array PSK signal. So you can see that from this figure that S0 2 up to S1, S2, S3 and up to M minus 1. It means total what? M symbols are there, right? And this is your axis. This is for reference axis phi1, and this is your phi2, which is given by this equation, this. And you can see the angle between these two symbols, it is what? 2 pi by m. It is differentiated by this what? 2 pi by m. So this is your geometrical representation of your M array PSK. So in examination, if it is come, then you have to draw this figure. And you can see that the distance of each M array PSK waveform, these are going to represent waveform, PSK waveform, M array PSK, S0, S1, S2. From the origin, you know the distance, it is what? Root of ES, as just we have seen. So what we have seen, just we are trying to, you know, represent it what? Geometrically. So hope so you understood this diagram. Now moving towards the next point. Now how to find the Euclidean distance, right? Now the distance between the signal points, is also known as what? Euclidean distance, which is represented by small d. This distance, guys, you know, it is very important factor in deciding the error probability of your communication system, because the error probability, it goes on decreasing if this distance is going to increase, right? So you can see this angle theta, it is nothing. See this angle that I already told, the angle between these two ary PSK waveforms or symbols, it is given by what? 2 pi by m. In QPSK we have seen it was what? 2 pi by 4, right? So 2 pi, 2 pi, it is going to represent what? Complete circle, and m, it is the number of messages. So you have to draw the circle. How to remember 2 pi? 2 pi, it is going to represent what? 360 degree. So 360 degree, it is nothing but your just a circle, it is there, complete circle it is there, and we have to divide this circle into a symbols, into a segments, which is nothing but how many symbols? It is going to tell you this value m. So m is 4, it equal to there, then we have to divide into 4 parts. If it is 16, then 16. Understood? Now we are going to find the now Euclidean distance. So as we know that sine theta, so over here theta, it is nothing but your pi by m. How to find it? See, we have drawn this perpendicular line onto this base, that is S1 S2, this dotted line. It is a 90-degree angle, and this is your theta. So sine theta, over here theta, it is nothing but what? Pi by m. Why? Because sorry, this theta is a what? 2 pi by m. This is 2 pi by m, but we are going to take this angle, so it would be divided by 2, so it become what? Pi by m. So sine of pi by m, how we are going to find it? As it is nothing but the reciprocal of the ratio of what? Distance, that is S1 x, that is a base, upon this distance, that is your distance origin O to S1, that is your hypotenuse, right? Now, so this sine pi by m, what is this distance S1 x? It is nothing but your what? D by 2. Since it is total, it is what? D. So the half of it would be D by 2. And as we know, the duration, the distance of each symbol from the origin, it is given by root es. So D by 2 upon root es. So we can rearrange it as we need to find the D. So D, it would be what? Twice of 2 square root of es sine of pi by m. So it is one of the most important. So you can see this one. So hope so you understood how to draw this or how to find this Euclidean distance. Now moving towards the power spectral density of your M array PSK. Now if you remember the power spectral density we have written for QPSK, it was what? The combination or adding of your even bit stream and odd bit stream. So what we resultant power spectrum density, what we got? Power spectral density, it is what? 2ps ts sine of pi f ts by pi f ts, that is, it is nothing but your sinc function, right? Sine of theta by theta, it is nothing but your sinc function whole divided by 2, and hence power spectral density of M array PSK, its shape also going to resemble to what? Sinc wave. So now putting this ts equal to what? NTB, because as we don't know, right? So over here, since ts equal to what? NTB, n, it could be the number of bits, right? So putting that NTB in this previous equation, so this new equation that you would get it, it is for what? M array PSK. So ts is replaced by what? NTB. So ts is replaced over here what? NTB. So this is the power spectral density of your what? M array PSK. So this is the PSD of your M array PSK. So you can see it is a sinc function, it is there. 1 by Ts and it is a minus 1 by Ts. So bandwidth, we can find it by 1 by Ts minus of 1 by Ts, right? So hope so you understood. And 2 Ps NTB, it is nothing but your this amplitude. So y-axis, it is your power spectral density versus with your frequency, right? That is fs2 minus fs, it is there. So now how to find the bandwidth? As we know, bandwidth is equal to 1 upon Ts minus 1 upon Ts. So it would be what? 2 by Ts. But Ts equal to what? It is NTB. Since we are going to put Ts equal to NTB, or we can write it as we know that 1 upon TB is nothing but your FB. So we can write it bandwidth is equal to what? 2FB upon N. It means, as we know, 2FB, it was the bandwidth of your BPSK. So from this equation, we came to know if the number of bits per symbol it is going to increase, then the bandwidth requirement it is going to reduce. So this is an important conclusion, that if the number of bits per symbol it is going to increase, then the bandwidth requirement it is also going to what? Reduce. Now moving towards the advantages of your ary PSK. So ary schemes are preferred to the binary schemes when we want to conserve what? Channel bandwidth, as we just seen now. So bandwidth reduces with increase in number of bits per symbol. As the information unit is transmitted through this signal phase, not through signal amplitude, the system it is going to operate very well in the solution where the signal amplitude varies due to the characteristic of transmission medium. So even the noise it is being going to add onto its amplitude, but our digital information it is going to be invariant. Moving towards the disadvantage, we are going to achieve the bandwidth conserve, we are conserving it, but at the cost of what? Increase in transmitted power and increase in error probability with increase in the number of bits n per symbol, as the distant D unit is going to increase in n number of bits. And third, that is the transmitter and the receiver of ary PSK is very complex. So guys, today we have seen what? ary PSK. That QPSK, as we know, it is a special class of ary PSK. But if the number of bits it is more than that of 2, then how ary PSK? Then how we are going to generate ary PSK, its coherent detection method. Then we have seen the geometrical representation of how we are going to represent it. Then we have seen how to find the Euclidean distance. Then we have seen the power spectral density of your ary PSK, and from that we have found what? Bandwidth, that is 2FB by N. So bandwidth it is going to reduce as the number of bits per symbol it is going to increase, right? So this is your assignment. So please note down this assignment. In next module, that would be the last module of this unit number 5th, that is ary cam quadrature amplitude modulation, its generation, detection, and advantages and disadvantages of it. This is the email address for any questions and feedback visible on the screen. So thank you very much guys for today's lecture.